All righty. Good morning, everybody. How are you? All good? 2.5 days in, still have energy? All right, cool. Excellent. Yeah, welcome to a new era of cross-domain diagnostics, and let's look at what we can go and do there with AI, classic ML, and more recently, agentic systems. So I want to go and take you a little bit onto a journey. But before doing that, my name is Frank, and I'm working as part of a division inside Cisco that is called Outshift. So not oh shit, but Outshift. And we are working on emerging tech and incubation of that emerging tech. That means everything that I'm talking about is tech-focused and not product-focused. I'm not talking about anything that you can go and buy. Disclaimer, right? Even if I'm showing you kind of cool demos, sometimes you can go and clone the stuff on Git, but it's not yet available as a product. So what I want to go and focus on today is this problem and turning that into something meaningful. If you look at a contemporary XR router, for instance, like a Cisco 8000, it easily has more than 1 million counters available, plus log files, plus its config. Does anybody look at that 1 million counters? No. Can you even retrieve all that 1 million counters instantaneously, say, every 10 seconds? Probably not. You're going to overwhelm the device. But there is a subset of that you might retrieve, and how do you make sense out of that? And how do you make sense out of that so that you, as a human, can naturally ingest it and digest it? I.e., we want to go and have this thing talk to us eventually in natural language. And maybe you don't want to go and look at that device in an isolated way, but you want to go and look at it across multiple systems, but still reason about the state of the system in natural language, which is our way to go and reason about stuff, instead of like looking at time series and alerts on time series and the likes. So that's what we want to go and explore over the course of the next 60 minutes. And I want to go and have you keep a mental model in mind while we're doing that journey together, which is how we as humans interpret and reason about data. We don't really correlate data points on time series, right? What we do is we look at a dashboard, we look at log files, and then we translate that into our interpretation, which is natural language. And then we form a conclusion from that data, and we might even share that conclusion with other people, form hypotheses of what's going wrong. If somebody tells you the printer doesn't work, you might have heard that phrase. I've heard that phrase 1 million times. And it's typically not the printer that doesn't work. And we need to go and figure out why the printer doesn't work. Is it the network? Is it the spooler? Is it the server that the spooler runs on? And the likes. And if we are troubleshooting, we are looking at this individual domains of data, and then we're kind of comparing that data in our mind. And again, we're doing that in natural language. And we have a great vehicle these days. And that great vehicle is called large language models, which is able to go and translate stuff into natural language. So can we use that vehicle so that computers can do what we do in our minds today as we're interfacing with each other and troubleshooting and diagnosing things? That's exactly what I'm after. So let's start with a very simple example, and then we're growing that example in complexity. So we're starting off with diagnosing logs, which are almost like natural language, so semi-structured, with the help of AI. And hopefully most of you in the room have done that. Then we're up-leveling the whole thing to go and see whether we can go and do the very same thing, i.e. translating time series into natural language with diagnosing streaming telemetry from a Cisco device or a set of Cisco devices. And then we're up-leveling that again and trying to go and do this across multiple domains, multiple layers. So let's start off with something simple. And the something simple is logs. So imagine, put your shoes into an IT ops engineer. Somebody threw you a file, and that file might be called clubfanel blah, blah, blah.log. And then somebody's asking you, like, what is the issue? And that file looks like this, right? So just a log file from Kubernetes. So what would you do? Well, you would probably use your favorite tool to go and a little bit sieve through the data and see whether you can go and get an idea what's going on, right? So what I would do is I would go and grab for error or traceback or warning, and hopefully I find something. Is it the right thing? Maybe, maybe not. Yeah, I could do that. Maybe I'm successful. But how about we ask AI to go and do that? And the super simple idea that you might have by now is just like, let's take the log file, cut and paste it into ChatGPT and see what ChatGPT will make out of that. That might work if the log file is small, but in my case, I up-leveled the problem a little bit and said, well, let's take a log file that is not super small, but my log file here translates into 4,500 lines. And if I tokenize that, that's roughly 200,000 tokens, which is beyond the typical size of the context window of, say, ChatGPT 4. Now you can argue, say, well, maybe, Frank, I can go and use Gemini, and that has a 1 million tokens token window. That's not my point. My point is, I'll find you a log file that is bigger than your token window or your context window. So what do you need to go and do with that? Well, we need to go and somehow filter this file without really losing the core information in the file, right? So let's see whether we can go and find easy ways to go and get the redundancy out of this file, out of the log file, and keep the key information in that file. And yeah, well, there's multiple ways on how you want to go and do that. There is statistical approaches, and we're going to go and use a very simple statistical approach in a minute to go and filter that file, where you're just saying, well, intuitively, if you look at log files, we know that there is these log files that have a load of redundancy in there where a process says just like, hey, I'm alive, hey, I'm alive, hey, I'm alive, and this does every 10 seconds. Is that super useful? No. It's good to hear that once, but not 1 million times. So there's a load of redundancy in there, which is why statistical methods are quite useful for filtering purposes. Sometimes this is not good enough. Because like even if you filter, you can go and filter it down, but then the substrate that you're arriving at is still too big. Maybe you need to go and have additional approaches, and these additional approaches are all based on you're creating a projection between the original space, i.e. your original log file, into some vector space, so that in that vector space I can go and cluster the data, and I can go and cluster not only about attributes like statistical occurrence, like which is what you would do with the statistical approaches, but I can go and cluster even based on semantic correlation. And that leads to approaches where we do using embeddings to use clustering, like with Logbird, LogBD, and the likes, so that you can go and filter further with those approaches. But, well, the simple approach will do in our case. And I'm using something very simple here. As I said, I'm using a mechanism that is probably well known or intuitively being used by many of you. If you read an abstract of a paper, that abstract contains a couple of keywords. And these keywords, how do we arrive at these keywords? Sometimes the keywords are human-generated, but in many cases these keywords aren't human-generated, but a system did that. What are keywords that are meaningful in a paper? Keywords that are meaningful for a paper are words that are frequent in this particular document, but they are rare in all the documents that you have. So a measure of importance is when you frequently see a particular term in this particular document, but when you read all the papers, this term isn't really occurring quite frequently. That's a meaning that this thing is something that is unique to this particular paper. And we're using exactly that method with term frequency and verse document frequency. That just means if a word appears frequently in your document, you assign it a high score because this seems to be an important word. But if this word appears in a load of documents, then you assign it a low score. And then you combine these two scores. And that's a pretty nice meaning, because like, just think of something. If a word appears frequently, like the word the, it's appearing frequently, but it also appears frequently in a load of documents. So if you combine the two, you want to go and score it down. But if there is a term like large language model in your paper, and large language model is not frequently appearing in all your documents, then you want to go and assign it a high score. So what is behind that? There is an intersection of two distributions. And I need to go and come back to that later on, which is why I'm spending a little bit of time here. There's this one distribution in the corpus, all documents, and there is the other distribution in your particular paper. And you're defining the intersection of this particular set of two distributions. And a measure for that intersection and the importance of a particular word, or the rareness of a particular word, is a direct correlation to the cross-entropy between the two distributions. We'll come back to that later on. So if we use TF-IDF on our particular document, that just means we are seeing that a log line in here represents our particular document, and the entire log file, so all the individual lines, represent our corpus. And then we use TF-IDF as a sorting metric. So the outcome of that is that rare log lines will bubble up to the top, and things that are frequently seen will sink down to the ground. So this, hey, I'm alive, hey, I'm alive, hey, I'm alive, it will sink down to the ground. This one thing that you only saw once will likely top out. So that's exactly what we need, right? So that the redundancy stuff sink into the ground, and the stuff that is very frequently happening is going to the top. And you can go and further improve that. So if you look at how you tokenize, some things are very related, right? If you consider the stemming of a word, then you can go and make that one token instead of multiple. We can improve that, but I've not really done that here. If I look at this, sorry for the fine print, left-hand side is unsorted, right-hand side is sorted. And if I zoom in on the sorted side, what tops out at the top 10 is, yeah, there's a couple of things that are still like, bootstrap done. This is rare, but not too interesting for me. If I read through this, yeah, there are a couple of things like false learning, maybe. But there is something here, no subnet found for key. If I know Kubernetes, I know that, yeah, that might be it, right? But maybe you don't know Kubernetes that well, and you still don't really have an idea. And by the way, like if I filtered with grep on warning, error, none of this tops out, right? So now, idea is, this is very little, right? So we can go and fit that into any language model, even with very small context windows. Not a problem. Let's do that. I did that with ChatGPT 4.5, so a very recent one, where I say, well, you're an IT ops engineer. Your task is to diagnose an issue described on an excerpt from a log file below the 3 hashes that I'll see further below. And we retrieve that, sorting the log file using TF-IDF as a metric. And now please go and perform the following task, one after the other. The first one will be to go and create a technical description of the problem in less than 100 words. And also consider the name of the file, please, because that has information in there. And then go and tell me what to go and do about that. And the interesting thing is, if I now also paste, obviously, my 10 lines that I filtered out. So there is the information that I filtered out. As we saw before, if we click on Go GPT, run for me, it will very swiftly say, well, there is an issue that occurs with the Kubernetes node. So it forgot all about that bootstrapping stuff. It was safe to ignore that. It really honed in on flannel subnet configuration. And, well, it indeed saw that it couldn't really correctly obtain subnet configuration, so that was indeed the issue. We forgot to configure Kubernetes subnets in this particular point, and then it tells me what to go and do to look into the flannel config map configuration to make sure that I have subnets configured for v4 and v6. So that's exactly what needed to happen. So conclusion is LLMs do understand log files. So the corpus of the training data of a large language model like GPT-4 completely includes information on a load of log files and training data. So it can go and diagnose these issues very nicely. That's good. So we can go and turn logs into a natural language description that we can further reason about. First stepping stone done. Now let's up-level that conversation. Let's make it harder. And look at the whole thing from a streaming network telemetry perspective, so time series. And what I want to go and do again is, let's see if we have a set of time series, many time series, can we go and translate what is happening in this time series, or this set of time series, into natural language. So what we're going to go and do is, spoiler alert, we're trying to go and see change points or anomalies in these time series. Once we find the change points in the time series, we're trying to go and associate these change points with something that is semi-structured. And something that is semi-structured is the name of the time series that are most descriptive for a particular change point. And once I have the set of names that are describing, or the set of counters that are describing a change point, I'm trying to go and turn that into a diagnosis for the change point. And apparently that works. So if I'm choosing the right counters for a change point, the names of that, I can have an LLM explain me what's going on. We'll see that. But let's get there. Getting there also means we need to go and do a little bit of, well, classic ML to go and get there. So again, let's start with this, like, imagine you're an IT ops engineer, and now you're tasked with troubleshooting a set of network issues. And what we're starting off with is we gathered a bunch of streaming telemetry information from a system, and then we need to go and draw insights into that. That's my system. So there's a lab setup we had in Building 9 in San Jose. So classic leaf and spine, two-stage class, fabric, runs BGP in that fabric, all 100 gig uplinks. And what we've been doing is we've pushed traffic into that fabric with Ixia traffic generators from left and right. So we pushed traffic into that fabric, and then we created a set of artificial or synthetic events between this device here, spine 4, and leaf 8. And our job will be to go and re-retrieve these events by just looking at the data, streaming telemetry information, time series information that we extracted from that system. So we're exporting telemetry information from that particular system, and we just have to go and look at that information and see whether we can re-retrieve whatever I did between these two systems. So what did I do between these two systems? Up here, I started IX chariot traffic, so I started the Ixias. Then I broke, quote unquote, my BFD session. I broke BFD by putting an access list in that filtered out BFD traffic so that the system felt like, yeah, BFD is not working anymore. Then I shut down an interface. I re-enabled BFD. I re-enabled the interface. So I created all these set of events between the devices spine 4 and leaf 7, as you see on the various interfaces. So relative second 6, broke BFD, relative second 1200, shut down the interface and the likes. So this is the set of things that I want to go and re-retrieve by just looking at the data and then say, well, can I go and really tell us that we broke BFD, for instance, at that particular second? So what I did do is I subscribed to a bunch of sensor paths to retrieve telemetry from that system. This is the set of 24 sensor paths that we subscribe to. So, and it's I think it's a good mix that you typically see in a streaming telemetry setup. Starting all the way from kind of memory stats, WD Sysmon, then you have V4, V6, IO Oper stats, you have FIB stats, you have BGP and BFD stats, all the way down to the Ethernet driver level here. If you do this, 24 sensor paths, yeah, there's quite a few leaves in these Yang models that you have out there. So if you do this and you retrieve that information every 10 seconds, this is the data set that you arrive at. So ultimately, given that there is the timestamp here, it's 7,333 individual columns. So it's pretty high dimensional. So we're dealing with more than 7,000 individual time series. And as a human, it would be very difficult to go and read these time series, right, and see what's going on. So it's a way harder problem than looking at a log file. So we need to go and do something about that, and we want to use ML to transform that into something that we can then later on feed into a large language model. This is what the data would look like if I just plot it. Do you see a pattern? Do you see that we created an event here? No, right? It's like rubbish. It's random rubbish. So very high dimensional, high number of features, and the problem is that not all of these things are created the same, right? So some of them are counters that are on and off, like is the session up or down. A load of the counters are incremental because they are related to traffic. So it's all kinds of nature and units. So we need to go and make them comparable, and that is what we need to go and do with pre-processing. So we need to go and clean that data a little bit, and then make this data comparable so that we can start to reason about this. Once we clean the data, we are going to go and try to go and detect what some people call anomalies. I think the better term for that is a change point, because not every change point is necessarily an anomaly, right? It might be like, yeah, well, everybody ended up going to the office at 9 a.m. because there is an event. Is that really an anomaly? Yeah, you saw a spike and everything changed at 9 a.m., but I wouldn't call that anomalous behavior. We're just going, yeah, well, everybody arrived at the office, but it is a change point for the network. We're going to go and detect these change points, and then the big leap will be how do we diagnose and describe these change points? Because that something happens is what you typically see in a load of the systems that send you alerts, right? 1,000 eyes, whatever. It sends you an alert, and your whole screen is full of alerts. Something is going on. We detected something. But tell me what happened and why it happened. That's the harder piece. So we get data from various sources. So these are like all the individual things that we would get from subscribing to the individual sensor paths. So we get a CSV file per individual sensor path, and we need to go and merge that. So that's easy. Once we merge this, we're still not done, because if you look at how XR collects telemetry, what do you believe is more important for a router, collecting information or forwarding packets? Forwarding packets, right? So what do we prioritize in the router? We prioritize forwarding packets, computing routing protocols, and the likes over collecting telemetry. That means even if you tell the router collect every 10 seconds, it might collect every 10 seconds. It might also collect things every 10.5 seconds. It will collect whenever it has time, right? Here above, you see like there is sometimes a delta of 13 seconds between the collection, 12 seconds, 10 seconds. Here, this is more accurate. Up here, it's less accurate. That obviously screws you if you want to go and make things comparable, right? So first thing is we have to go and interpolate things so that I can go and really align things on that particular journey and the various time points. So I knew to do this, so I interpolate and make sure that everything is 10 seconds apart. First cleaning step done. So a load of that stuff is no rocket science, tedious, but unless you do this, you're going to go and confuse yourself. So next thing up is not all the counters are created alike. So you have things that are monotonously increasing, like stats from interfaces. So almost everything that is traffic related always goes up. The question is, how fast does it go up? And then you have other counters like BFD session counts that go up and down. How many sessions do you have? Yeah, you lost one, you're down. You recreated one, you're up one. So that's more like status information. How do you make those comparable? Well, we differentiate those so that we only look at change here, because this is also only about change. And if we're only looking about change, then we can go and again make things comparable. So we need to go and differentiate. And then we need to make sure that numbers are looking alike. And that's the scaling piece and a little bit of smoothing. So scaling things so that everything's fitting into a window between 0 and 1. We do this almost everywhere. Even if you look at like large language models, the last stage is usually softmax, right? Where we're making numbers individually comparable and fitting them into an interval between 0 and 1. We do the same thing here. We smooth, and in order to make monotonically increasing numbers comparable to status numbers, we differentiate. After doing this, our time series go from something like this, if we differentiate, to something like this. So you don't see any pattern here. But here, you clearly see a pattern, right? You see that some time series, that was on, it started to increase, and then it dropped off again. This is all hidden in the noise here, because these are all like counters that are in the billions. If we do all of this finally, well, this is what we arrive at, right? So we now have time series, again, 7,333, with numbers all in the range between 0 and 1. Pre-processing step done. Now we can go and see, can we interpret that data? And interpreting that data would mean, like, we need to go and make sense out of a problem that has more than 7,000 dimensions. Can you imagine a room that has 7,000 dimensions? 3, okay, fine. Einstein told us that the space is bended in the 4th dimension. Like, yeah, the faster you go, the different the time feels. Okay, maybe we can even imagine that one, but 7,000 dimensions, it's going to go blow my mind, right? As a human, that's a real problem. Luckily, the problem isn't that hard. So Jen Rexford and team, quite a while ago in Princeton, have done research on what network time series data really looks like and how it's structured. And yes, we have millions of counters in a router, but all of these counters are highly correlated. So if you do principal component analysis, so if you look at the energy of the system and see how many dimensions you would need to really describe most of the energy of the system, then you find that this isn't a really high number. So what they've done is, back in the day, like I think this is work from 2007, they looked at Abilene those days, and they saw like how many principal components, i.e. dimensions, do I need to capture, say, something like 98% of the energy. So you're in kind of roughly, say, 10, 8, 9, 10, 15, depending on where you look at, individual dimensions to go and describe most of the energy of the system. That is awesome. Because that means your problem is not 7,000 dimensional. You just have to go and find a projection from the very high dimensional space into a lower dimensional space where it's way easier to reason about the data. And if your problem is like our data here, not too sophisticated, we can use a projection that even humans can comprehend. So there is a bunch of mechanisms to visualize high dimensional data, and using projections that humans can go and comprehend. What can humans comprehend? 2 and 3 dimensions, right? So let's see whether we can map things from the 7,000 dimensions into 2D, keeping in mind that it might actually work because the problem ultimately is not very high dimensional. So the idea is to use a projection, and there's a couple of candidates out there. One is t-distributed stochastic neighbor embedding, or t-SNE. UMAP is another method that is working alike, by the way. It's nonlinear. There is a little bit of simulated annealing in there. But what it does is it keeps the structure of the data intact while it does the mapping. What does that mean? If I have 2 points that are very far away in high dimensional space, they will be very far away in my map. And if I have something that is very close in high dimensional space, they will be very close in the map, in my 2D mapping. The distance between these, well, it doesn't really mean much. So what is far away, whether it's 10 centimeters away or 5, that doesn't really tell much. But what I'm really interested in is in the structure of the data. And if we map out my data set that we've seen earlier on, and even I'll put that as an animation here, well, the first thing that you see is there is structure. And as a data scientist, this is an aha moment. You say, wow, it makes you smile. It makes you really smile. Because you saw that there is a starting point, and then the system is in relatively stable state. Then I see a hop to another stable state. Then I see another hop to another stable state, and so forth, right? So there is stable behavior of the system, seemingly. Then, well, I jump to another stable state, then I jump to another stable state. And then what I did here is I highlighted some of these states. So the projections, every one of these dots is the projection of this high-dimensional space onto 2D, right? Remember. I highlighted those little dots here and then the timestamps here for that. And guess what? If we look at those individual points in time where something happens, this thing maps or correlates one-to-one to when we did change to the system. And again, I didn't only find structure. The second thing that made me really smile brightly is it even correlates to my events. This is freaking awesome. Because now I can say, well, I now know, I don't know what happened here. This is still not known to me, but I can retrieve these individual timestamps in the system by, well, just clustering the data, right? So I can use something in this projection, like dbScan, to go and retrieve these clusters, and then I know when change happened in the system. I can go and retrieve these change points. That's excellent, right? So we are one step further. So we had 7,000 dimensions. We didn't know what's going on. Now we know when certain things happen. And that's what a load of the systems out there do when they call it anomaly detection, right? Sometimes you're detecting anomalies based on thresholds. But defining thresholds for 7,000 individual counters, good luck with that, right? You're busy for a while. So that's a way to go and detect these things. So we can detect these changes. Can we also describe the changes? So maybe you say, Frank, how about we look at what changes at a particular change point? So just extract the counters that change at that particular point in time. Intuitively, great idea. We tried the same, but this is a plot of the orange line up there. So this line, I'm not tall enough. That's 7,333, so this is the number of features in the system. And I plotted here the number of features that change from time step to time step. So roughly 5,000 features change from time step to time step. That means change is the normal for a router. Why? Most of the counters have something to do with packets. Why do we use a router? To forward packets. So just using change is not good enough. And by the way, all these vertical lines are when I introduce a change to the system. And you don't even see that there is a massive pattern around these individual change points. So that doesn't help either. So I need to go and be a little bit smarter about that. And that's actually a hard problem. What do you do if you have a hard problem? You find a smart PhD student to go and look at that for 3 years of his life. Thomas Felton, colleague of mine, did that. And so we had two intuitions when we started that off. First, change isn't equal to change. Sometimes change means a spike. Sometimes change means a step function in the amplitude. Sometimes change means a change of frequency. That's already helping to go and qualify what matters and what doesn't matter. For instance, a spike is largely not interesting because there's all kind of randomness and noise in the system, and so these spikes are not really helpful. A step function is very helpful in most of the cases. And the second thing was this intuition of not every counter has the same amount of information or information content in it. So there are some counters that are there, but they don't really carry a load of information, while other counters carry a load of information for your overall system state. And if you look at Yang, the name of a counter is fairly long. So the intuition was, can we use the name of the counter along with its occurrence to go and qualify whether that counter is important or not? So we're coming back to this idea that, and that's why I spent a little bit of time on TF-IDF earlier on. We're applying the TF-IDF idea to the names of time series or counter series. So if you have something like TCP connection statistics, 100 gig E byte sent, boy, you see this thing all the time. That's not really interesting. It's probably low importance. But certain things like interface summary, admin up-down, you rarely see that. So that's more important. So we are again taking rareness as a means to go and qualify whether a counter is important or not. So the general idea is exactly what we had with TF-IDF. So if I see certain tokens very frequently at a particular point in time, but overall, they're hardly ever seen, this is key information. If I see something all the time, it's kind of, yeah, fine. So, narrowing down a little bit things, the first problem is specificity. So anything could impact a change. So anything, all the events are equally likely, like BGP events, ICMP events. So the level of surprise to any of the counters is equal. So there is not a load of like information content in this because everything is equally interesting, seemingly. Here, if you see a load of stuff on BGP, then very likely there's something happening around BGP. So you can look at that occurrence first time. And if you just look at the entropy of those, like entropy in information science is, well, the level of surprise or uncertainty relative to the random variable's outcome, right? So if something is equally surprising, the entropy is relatively high. If there is little surprise in the outcome, like here, it's almost always BGP, then the entropy is low. So entropy describes the focus of a particular selection. The second thing is, how do I compare things? Like if something in the full distribution, so in my corpus, is distributed like this, so a load of BGP, a little bit of BFD. In my selection, there's a load of BGP, and again, a little bit of ICMP and BGP. That means like, yeah, well, we favor the BGP piece. But it's even more important if you see something that is rare in the overall corpus and very frequent in my individual selection. So it's exactly the same idea that we have with TF-IDF and is something where we can use cross-entropy between these two distributions, between the selection and my corpus, to go and derive that importance of that particular feature. And now we're blending this, so the importance metric with my earlier, like, is it a spike? Is it an amplitude change or a step function? We're blending these two things together. And as we blend it together, magic happens. It's like, it's really magic. So you look at a particular change point where we broke a BFD session, and if I sort my 7,000 time series using this metric for where we broke BFD, what pops out? 5 BFD session counters related to BFD session counters and BFD neighbor changes. So just looking at the amplitude and the type of the amplitude change, plus how rare a particular counter is in the corpus compared to a particular change point, carries a load of information value. And now, well, the next step is ask an LLM to go and interpret that, right? Because you might be not that fluent in Yang. You want to go and interpret that. Again, you're saying, well, you're a networking expert. You're diagnosing a network issue using streaming telemetry from a Cisco router. And below, you have a list of sensor paths or the names of the sensor paths which have changed the most while the change occurred. And I'll also give you a little bit of indication how much change there was, because I'm dovetailing the whole thing with the word change and then putting the amplitude of change. And here's the list of that are most descriptive for that particular change. And then we're asking it again to do exactly what we were asking for the log file. First, go and describe what the issue is. Come up with a description. Be technical and specific, single paragraph, please. So don't really re-explain BFD to me, for instance. And then come up with a resolution description suggesting steps to fix the issue. And, well, then obviously I'm missing here, still need to go and cut and paste, my set of sensor paths that, plus the word change at the very end here, that describe what that change point was all about. Again, asking GPT 4.5 to go and generate that. It came with, it's like the telemetry indicates that there is a bidirectional forwarding session issue on that particular interface. It now honed in on like session state up and down, and then it tells me exactly what I would need to go and do in order to troubleshoot that. What would you do if you would see a BFD session down? We would look at the physical connectivity. You would see whether the counters on both ends or BFD is symmetrically configured. So that's exactly what it recommends doing. So what you've just seen is, if I automate that, is I throw the thing 7,000 time series, and it arrives at a description of what I put in as change in natural language that I can read and interpret without even understanding Yang. I find that quite cool as a data scientist. So, but yeah. And as a network engineer, even more so. So the thing is, an LLM understands Yang, IT networking, and it can help us interpret these events very granularly. By the way, if you try this, and you try this with GPT 3.5, you'll be frustrated. If I first tried that, like a year and a half, almost 2 years ago when GPT 3.5 came out, I was working on that. I thought, like, yeah, maybe I can do that. And I had to go and tell it, here's a snippet from the Yang RFCs. Here is a snippet that explains to you, here is how you want to go and look at the Yang tree. It didn't really work. Why? Because the training corpus wasn't large enough for GPT 3.5. When GPT 4 came out, I almost had a party, right? It was a game changer because like the number of parameters is tenfold, almost like 1.75 billion compared to what you had with, trillion, sorry, compared to 175 billion in GPT 3.5 land. And it knew Yang. It knows RFCs. It knows streaming telemetry. Very cool. Now, if you're interested in trying that yourself, I put that up roughly a year ago on Git, so you can go and play around with that exact example if you want to. Yes, please.
Have you tried the deep networking model that they're hyping at the keynotes?
So have you tried?
The deep networking model that they've hyped at the keynotes.
So question is, have you tried the deep networking model that they hyped at the keynote? The answer is no, because it wasn't available until. So that is a very recent development. The deep networking model is fine-tuned on CCIE-type data. I would expect that this is even smarter, that we can go and push it a little further. But even those results are, I would call it, pretty good, right? It might well be that you're having very specific Cisco events that this deep networking model that we just announced would do even better. You can play that with that. If you're interested in playing with this a little bit yourself, there is a feature that I built a couple of years ago in iOS XR. It's shipping since 7.3.1. It's called AI-driven telemetry. What this thing does is, on a Cisco router, You can go and obviously export all the sensor paths and all that information. Maybe you don't want to go and do everything and export everything, but you want to have the router pre-filter and understand only if there is a change that you're exporting the most relevant information about that change. So exactly what you had, all the journey that I took you through, up to the point where we put the thing into a large language model. That's what you can go and do around a router, right? So you can go and look at the ADT, AI-driven telemetry events. So you're not exporting everything, but you have certain events like around addressing or traffic and reachability. And then you can export the individual sensor path information. I like streaming telemetry, but it's very focused streaming telemetry. Instead, you're not drinking from a high fire hose anymore, but like you're just drinking from a fire hose drip by drip.
Can I have a question?
Yes.
So does it mean ChatGPT 4 or 4.1 is trained with all the logs or only the change point-based troubleshooting?
So question is ChatGPT trained with all the logs? Very likely, ChatGPT has seen more of the world of networking than all of us together, because it has seen networking logs in northern Mongolia, southern China, northern Japan, southern Europe, Canada, the US, wherever, right? So it has all that information likely in the corpus. And so it can know and interpret all types of information moderately. We still have to go and find the change point, right? So that's our task. We have to go and distill. So the heavy lifting is indeed what I did prior. Detecting the change point and describing the change point with a few counters that then GPT is smart enough to interpret that, yeah, well, if you have these things, then likely this is the thing that's going on.
So GPT is trained with the change point-based prediction or troubleshooting.
Yeah,
Right? Something like
correct. So let's up-level the whole thing further. Let's go from single device, single domain, to how about we have multiple things going on all at the same time in multiple levels. So you have logs from Kubernetes, logs from the server, traces from the routers, and that's the typical thing that you see, right? Like somebody says, my application is not reachable anymore. Something went wrong, I can't print. Or I had a customer that has thousands of retail locations, and guess what? The typical trouble statement there is the Wi-Fi in the store is slow. And it's not like go and debug the Meraki access point. The Wi-Fi is fine. It's the SD-WAN connection, the data center load balancer, the firewall, the server in the data center that runs the application itself, it's somewhere there, right? But we have these, if we look at layer 1 support, we typically see these things coming in. So in my little example here again, I have an OSPF network, so there's a Cisco modeling lab, CML. We attached a bunch of VMs to that, and on the VMs we're running Kubernetes, and on that Kubernetes we have a Vote app, a simple front-end, back-end application installed that passes traffic between front-end and back-end all the time. And what we've done to go and simulate a failure is we filled up the disk of one of these VMs. And we also defined the affinity rules the way that Kubernetes has to schedule the pod on that particular device. If the disk is full, the pod gets ejected, it puts it back on. So what happens? Like, you're losing connectivity. So it's a disk full problem, but the customer sees that the application doesn't really work anymore. So can we troubleshoot that? So imagine you're that engineer, and you get this tarball, 6.5 megabytes, and that tarball contains logs from your application, so all the way, like, you see the services up here, like Redis and the likes. You see logs from the kube system. You see even kubectl commands. You see logs from the routers, show commands from the routers. You see server logs, all kinds of information. Somebody throws you a tarball, you're on layer 1 support, level 1 support. This is not fun, right? So can we build a system that helps us with that? So it's a little bit like what we had back in the past if you're doing cross-domain troubleshooting, and we still have that. So it's this blind man touching the elephant problem. So somebody says, I have a problem, but then depending on your visibility of your individual domain, you look at this from a server perspective or a network perspective, and how do you bring all of that together? There is multiple ways on how you can go and do that. One way is somebody tells you, like, all of your teams, you all gotta go and come together, and you put all your data into one big data lake, and then we create one big schema with one level of interpretation of all the data, and then we build kind of a rule set based on that and bring it all home. For some people, that works. But this kind of consolidate all your data into one data lake under one schema is super hard to achieve from an organizational perspective, which is why, in most of the cases, what I see today is we have people from the different domains, the server guys, the networking guys, they're all meeting in a room, and then they're arguing, and then they can go and figure out like why the Wi-Fi is slow, whether it's a server, whether it's a firewall, whether it's the SD-WAN connection, and you can do that relatively quickly if you look at the data in your domain, and your domain, and your domain, and then we consolidate. So how about we, rather than we have us meeting in a room for 30 minutes and figuring it out, how about we give that to an agent, right? So the schema thing, yeah, Satya Nadella said that very nicely. You said that schematize the world doesn't really work. So how about we have agents for us meet in a room, but troubleshoot like us. So, and that's an agentic workflow. What is agentic? I typically come back to the definition of what Andrew Ng is using. Not agentic is if you're asking an LLM to go and solve a problem soup to nuts with a single request. So that's as fair as somebody asking you to write an essay soup to nuts without using backspace. Who does that? So what would you rather do? You would do this in a collaborative way. Maybe like you write the first outline, then you do some web research, and then you write a first draft, and then you critique the draft. And language models are way better at critiquing something than building something, much like humans. We're also like punching a hole into something like, yeah, easy. Writing something, hard. And then you iterate, right? So you're creating something better. And these agentic systems, guess what? What will create the better result? This one or single shot? Much like humans, if we would collaborate, we would write the better draft, and agents are the same. And it's dramatic how much better agents get if they are collaborating. So GPT 3.5, not a good model for coding. Typical accuracy, if you ask it a coding test, we all remember that back in the days when Copilot came out. Like, not really good. Accuracy, roughly 50%. If you use agentic behavior, researchers have shown that you can push this all the way up to 95%, even on a quote-unquote not so good model. For the same story. So if we use agentic behavior, we can really improve how we operate in the system. And what are the design patterns? So somebody needs to plan. Somebody needs to form a hypothesis. Then you do something tool calling like web research or retrieving the right information from your backend systems. Then you reflect, i.e. you critique, and all of that in a collaborative way. And one important thing is also memorizing what you've done so far, because it's very, like with humans, it's very boring if somebody forgets what you told him like a second ago. Some old people are that way, and we all know what the challenges are communicating with them. Same thing with an agent. If you over and over and over have to tell the guy, like, look, no, you want to have the guy remember. So how do humans troubleshoot? We form a hypothesis or a set of hypotheses. Is it the network? Is it the server? So we're creating a kind of an intuition and a plan. And what do you do next? You're going to try to find information in your backend systems for your hypothesis. So if it's a network issue, you think it's a network issue, then I'm going to go and drill a little deeper and see, well, can I find something in the logs? Or if I believe it's a server issue, can I find something in the logs? If I find something in the logs about the network, then it might mean like, well, maybe it's this router. Then I'm going to go look into the router. And then I'm saying, well, maybe it's this interface. And then I'm going to go look into this interface. So I form a hypothesis, I retrieve information, I evaluate that information, and I might reformulate my hypothesis, and I'm iterating, right? That's what humans do. Can we do the same thing with agents? That's the experiment. So that means like we have agents collaborate on hypothesis building, so a planning thing, retrieval thing, evaluation, all the way up to not only if you have is it a server issue or is it a network issue, but also is the server issue that I find depending on the network issue or the other way around. So I also need to go and look into dependencies. So I have my diagnostic agent, I have a retrieval agent, and that retrieval agent will not only consider information from the systems, logs and live information, but also information that we have in our backend databases, like knowledge bases, like bug database, cadets, and the likes. Then we'll evaluate that, and later on we bring it home by summarizing. In order to go and understand that a little bit further, I want to go and show you an experiment that is almost a year old when we started to build stuff, and it went a little wild. So what is this? This is an investigation graph from roughly a year ago, where we started off with a particular problem statement up there. And that problem statement is my first starting point, where there. So this little star, where we say my vote application, available on port 31,000 is not reachable anymore. Then it went off and said, well, what is a potential hypothesis? Network issues preventing access. Yeah, it's a network issue. We could have found that, or inspired that, or the vote port has crashed. Again, it's an application issue. Not bad. But it's the LLM that came up with that hypothesis, right? It's not us. Or Kubernetes issues, potential misconfiguration, something going on in Kubernetes land. And the dark line is getting me to the success. So let's follow the dark line. Next one is, I formed that hypothesis, I retrieved data, and I found some information in deployments.json, so a config file, that allows me to reformulate my hypothesis, where it says, like, the service for the vote app is not configured correctly, maybe. I retrieve additional information, or try to find additional information for that hypothesis, and this time I found a syslog file, and this syslog file says, failed to admit port to node. Now that gets me a little closer. I reformulate my hypothesis, or I have it reformulate my hypothesis, and then I find that the node manager was low on resource, and that gets me to my final thing, where I say, the vote app, the node is experiencing disk pressure due to low ephemeral storage, which prevents the vote app from being admitted to the node. This is freaking accurate. So we have a journey that takes us all the way from the problem all the way to the endpoint. Now the question is, how do you find the right branch? And how don't you go wild? Because here we went wild, right? 2,000 calls, and what we didn't really do is we are not comparing things step by step and saying, well, is this dependent on this? Are there interrelations between these hypotheses? So is it the server, is it the network? Are these interrelated? So I can go and not follow the network hypothesis, because I'm pretty sure that what I see in the network is kind of originated in the server domain. So by the way, yeah, you can summarize all of that with an LLM, and it gives you a nice description. So we went one step further. So we correlated these things. We used additional backend data, additional context. We are by now using purpose-fit models for the various tasks, because like the standard language models not necessarily operate optimally on network data, because the tokenizer was trained on natural language. That means also that the semantic relationships that you have are based on what natural language is and not what system information, log information, and the likes is. So the attention matrix is optimized for natural language. It's not optimized for individual information that you see from logs and traces and router show commands and the likes. So bringing it home, here's a concept demo of a recent system that we've built to go and focus on level 1 support problems. I don't want to go and solve the super hard stuff, but I want to solve this stuff where somebody did a change and didn't tell the other group, and then, well, bad things happen. And we have our agents that we've seen earlier on employed there. So this is an experimental system where we see that we have a bunch of incidents listed here, like my vote application was down, BI report app is slow, and then we investigated those, like the status here, and we see the root causes that we found from in our systems, along with what we've seen earlier on, individual resolutions for that problem. Okay, we can go and dive into this because this is relatively clean. So this is based on synthetic data. My BI report app is very slow since yesterday, and the system came up with only two potential issues. One is a fan failure, and the second one is MongoDB being slow. And well, this is only with 40% confidence. This is with 90% confidence. And this is my investigation graph that resulted. And I can use this investigation graph and go and time travel back a little bit of how we came to that particular conclusion. So we started off with the initial problem statement. So the customer reported that the BI report app is experiencing slow page loads. So this is where we started. I need 2 more minutes, if you can bear with me. Is that fine? Then we formed a set of hypotheses, like BI report app failed to fetch resources, connection timeouts, slow MongoDB. We fetched resources, and we reiterated, and we changed the hypothesis to increase packet drop rate on router RE7. We fetched additional information on it. We reformulated the hypothesis, automatic shutdown on router R99. And then finally, we ended up with fan failure on router 99, and we couldn't really find additional information for that. So what happened is fan failure caused a router to overheat. That got shut down. That caused another router to be overloaded, which is why the application had so slow page loads. Kind of interesting, right? And you can go and bring these investigation graphs together in a natural way so that it's not going wild anymore. So when this was synthetic data, but we can also go and do this back in my original system, like front end, back end that we had, and this time we shut down a link between R4 and R6. And yeah, well, in order to investigate this live, what we typically have to go and do is first go and point it to the data to go and retrieve it from. And in our system, all the data is in Amazon S3. We're typically storing it there. You could go and connect to Splunk if you have it in Splunk. We can even use Thousand Eyes, as we show here, as a potential trigger source, so that I'm not kind of triggering it myself like you've seen it, but you get it from a backend like trigger source. Here I have my data in S3, access key, like region. I just need to go and configure the bucket name real quick. And then we are ready to go and start an investigation. So I can go back. I have my Amazon connector now in. I can start an investigation. And what I need to go and do there is, I need to go and give it a title, but what is very important is that I give it an accurate problem statement, where I say my vote application running on port 31000 is no longer responding. This is what gives it the information to form an hypothesis and then branch out. And then it's starting to investigate, and given that the data set is very small, and this is real time here, it's arriving at a conclusion very, very quickly, and the investigation graph is also very small, where you start off, and it arrived at the right thing, right? R4 gigabit Ethernet is administratively down. So we started with the problem is my customer application stopped responding, and then it sieved through the data. It found individual log files that describe R4 gigabit Ethernet interface being down, administratively being down. It found some other issues around a VM, but it was able to go and resolve these issues that the config of R4 being down was the root cause compared to this one, so it did the right dependency resolution in there. So net, I was able to arrive at that conclusion relatively quickly. Why? Because the underlying data set was relatively small. So bringing it home, we can go and do troubleshooting the old way, rules-based, like what you have with Catalyst Center Assurance and the likes. If I'm reasoning about data in a single domain, that's perfectly feasible because I have structured data with a schema in a particular domain, and I can go and do this like we do this like the last 20, 30 years. What if you don't have that information? Because it's information from multiple domains, multiple teams collaborating, then we can do it data-driven. And we can use LLMs to go and translate all that various information into stuff that can be handled across different domains. Data-driven. The only thing here is, this is fairly deterministic because we're following a rule set. This is highly probabilistic because anything that an LLM does is probabilistic. But guess what? Humans are probabilistic as well. LLMs hallucinate. Humans, maybe at times as well. Thanks for your time and patience. Some of that stuff is a little, techie. But I think it's a fascinating journey what we're up to, what we can go and do with LLMs. We're really bridging the gap. We're solving Conway's law, right? We're bridging things where typically like information doesn't travel, we can have that information travel in natural language. So all the stuff that we have as issues in an organization, maybe agents can go and help us with moving forward from a troubleshooting, but even like planning perspective. Maybe we can hand some of that stuff over to agents. And with that, continue to enjoy the show, the party tonight. The killers should be really cool. And I'm really looking forward to that. And yeah, thank you so much.